Unit 6, Day 2, Composition of Functions. Today you will evaluate and write composite functions. You will use composite functions to determine if two functions are inverses. The composition of functions uses the output from one function as the input for the second function. The order of the function operations is the same as the order of operations for numbers or expressions. The composition functions f and g is notated f of g of x. It is also equal to f parenthesis g parenthesis x. It means the same thing, f of g of x. Evaluating a composition of functions. Find the indicated value. Given f of x equals 2x plus 3 and g of x equals x squared plus 1. Find each value. So when you are composing functions, you want to start furthest inside and work your way out. So we're going to plug 4 into our g of x function, which means we want to replace our x with 4. Simplify that. So 4 squared is 16 plus 1 is 17. Then we need to plug that into our f function. So we want to replace our x in our f of x function with 17. 2 times 17 is 30. 4 plus 3 is 37. Example B, we want to evaluate our f of x function first. So we want to plug 4 in for all the x's in f of x. 2 times 4 is 8 plus 3 is equal to 11. We then want to plug that 11 into our g of x. So 11 squared plus 1, 121 plus 1 equals 122. In general, f of g of x does not equal g of f of x. So remember, order of operations is really important. So they, in general, do not equal each other. Example C just uses the other notation, f of g of negative 3. So we want to plug negative 3 into our g function first. So replace your x with your negative 3. Negative 3 squared is 9, plus 1 is 10. Then plug your answer from after you evaluated g into your f of x function. So 2 times 10 plus 3 equals 23. Example D, plug negative 3 into your f of x function for all of your x's. So if there were multiple x's in there, you would need to replace them all. 2 times negative 3 plus 3 is negative 3. We then want to plug that value into our g function. Negative 3 squared plus 1 is equal to 10. Finding composition of functions, you can use algebraic expressions as well as numbers as input in functions. To find a rule for f of g of x, substitute the rule for g into f of x. So the domain of f of g of x is the set of all x values such that x is in the domain of g and g of x is in the domain of f. So in example 2, we're given f of x is equal to x squared minus 4, g of x equals 3x minus 2, and h of x equals the square root of x plus 1. Write each composition of functions. State the domain. So f of g of x, essentially you are placing an x for all of the x's in g of x, which has already been done. So then we are going to take our g of x function and plug that in to our f of x. So wherever you have an x in your f function, you are going to replace that with what g of x equals. You need to distribute out 3x minus 2 squared. So that means write it twice. Do not distribute an exponent over addition or subtraction. 9x squared minus 6x plus 4 minus 4, so we get 9x squared minus 6x. Our domain for this, or the x values, could be all real numbers, as it is a parabola. In the next example, we want to plug h of x into f. So we are going to take our h of x and we are going to plug that in for our x's in f of x. So in parentheses, we have the square root of x plus 1 squared minus 4. When we simplify this, a square cancels out a square root. So we have x plus 1 minus 4, x minus 3. So our x values, we just want to make sure that the domain of h of x, if we have the square root of x plus 1, we cannot have a negative underneath our radical. So if we set this equal to 0, x cannot equal negative 1. So we want our domain is all the x values that are greater than or equal to negative 1. G of f of x means we're going to plug our f of x function into our g. So 3 times the quantity of x squared minus 4 minus 2. Distribute your 3x squared minus 12 minus 2. Combine your like terms, you get 3x squared minus 14. Our domain for a linear and a quadratic function is all real numbers. If we plug g into h, for example d, we are going to replace our x with 3x minus 2. Combine our like terms, so we get the square root of 3x minus 1. When we set 3x minus 1 equal to 0, subtract our 1, add our 1, divide by 3, we get 1/3. But when we set our original h of x equal to 0, we can't have x equal negative 1. So our domain, again, would be all the values where x is greater than or equal to negative 1. When both a relation and its inverse are functions, the relation is called a one-to-one function. In a one-to-one function, each y value is paired with exactly one x value. You can use composition of functions to verify that two functions are inverses. Because inverses undo each other, when you compose two inverses, the result is x. If you get the result when you compose your functions of x, then they are an inverse of each other, but you need to do it both ways. So if you're looking at f of x and g of x to determine if they are an inverse, you need to do f of g of x and g of f of x must also equal x. So let's take a look at this. If we are going to evaluate this first function and do f of g of x to determine if this is a function, if we plug our g of x function into f of x and solve, we multiply fractions, so we get 3 over 3x plus 3 minus 1. We get x plus 2. This does not equal x, so these are not inverses of one another. So B, for where x is not equal to 1 or 0, is f of x equal to 1 over x minus 1, and g of x is equal to 1 over x plus 1, inverses of one another. If we do f of g of x and plug our g of x into our f of x, we have 1 over x plus 1 minus 1. So when we simplify this, we get 1 over x. If I rewrite this as 1 divided by 1 over x to divide fractions, you multiply by the reciprocal, which equals x. So f of g of x worked. And now we need to go the other direction and plug f of x into our g and see if that works. So we need to test g of f of x. So we have 1 over x minus 1 plus 1. So again, if we divide these, we have 1 over 1 times our reciprocal. So we get x minus 1 plus 1, which results in an x. It worked, so these are inverse functions.